Did you know that by deliberately forcing a neural network to activate only a few neurons for any given input, we can make it extraordinarily good at spotting the odd one out in massive datasets? This is the unique power of sparse autoencoders. Imagine teaching a machine to summarize a complex book, but with a very strict rule: it can only use a handful of words in its summary. If a book cannot be summarized effectively with those few words, it immediately stands out, because it doesn't fit the expected pattern. That's essentially what a sparse autoencoder does with data. At its core, a sparse autoencoder is a neural network designed for unsupervised learning. It consists of an encoder that maps input data to a lower-dimensional latent representation, and a decoder that attempts to reconstruct the original input from this representation. The key differentiator is a sparsity penalty added to its loss function. This penalty discourages most hidden layer neurons from activating for any single input, forcing the network to learn only the most critical and representative features of the normal data. Why is this effective? Because if an input is anomalous, meaning it deviates from the typical patterns encoded by those critical features, its reconstruction error will be significantly higher than normal inputs. This difference becomes the unmistakable signal for anomaly detection. Consider its application in cybersecurity for network intrusion detection. Normal network traffic exhibits highly predictable redundant patterns. A sparse autoencoder is trained on vast amounts of this normal traffic, learning its compressed sparse representation. When an attack like a sophisticated DDoS or a zero-day exploit introduces unusual traffic patterns, the autoencoder struggles to reconstruct it accurately. The resulting high reconstruction error instantly flags the activity as suspicious, pinpointing potential threats that might otherwise go unnoticed. Traditional autoencoders might learn a broader, less specific representation of data, potentially missing subtle anomalies. The enforced sparsity pushes the model to focus intensely on the essential core of normal data, making it more sensitive to deviations. And unlike rule-based detection systems which require constant manual updates for new threats, sparse autoencoders adapt to evolving anomaly profiles, learning directly from the data itself. A lesser-known implication is that while powerful, tuning the sparsity parameter is crucial. Too aggressive and it might misclassify subtle normal variations as anomalies. Too lax and it loses its detection edge, yet this mechanism also offers a degree of explainability. The specific neurons that do activate for normal data often reveal underlying interpretable features that define that normalcy. This elegant technique demonstrates that sometimes AI's most profound insights don't come from overwhelming complexity, but from intelligent, constrained simplicity, teaching models to ignore the noise, and with pinpoint accuracy highlight what truly matters.